Hello everyone. I hope everyone is doing great. I am Radha Kumari Pani, Assistant Professor at Vedang Institute of Technology. So in last class we have discussed about the interfaces in material and how these interfaces plays the very crucial role in the phase transformation of any material, and also we have discussed two surface phenomena, that is surface energy and surface tension. Basically both have the same unit, that is Newton per meter. And today's class we will going to discuss, that is interfacial free energy. Okay, the term that is energy, that is energetically parameter term comes in today's class, and another one is bond breaking model. So what is interfacial free energy? Interface this it is known as the extra free energy that associated with any interfaces. Let here given one example, that is two differently both have the same composition. Okay, crystallite 1 and crystallite 2, but these are differently oriented. Their oriented direction is different. When they come put together, they form one interface known as grain boundary. In last classes we have discussed there are two types of interfaces is there. One is grain boundary, that is alpha alpha interface. Basically grain boundary is come because due to same composition, two crystallite of same composition, the interfaces is known as grain boundary. And if there is different composition, okay, two different composition crystallites there, then the interface is known as interface or alpha beta interfaces. So when the two different oriented crystallite come to put together, then one interface will come, that is known as grain boundary, and the expression of this grain boundary is G1 plus G2 plus Gxs. What is G1? G1 is the bulk free energy of crystallite 1, and G2 is the bulk free energy of crystallite 2. And here Gxs is known as the extra, that is interfacial excess interfacial free energy. Okay, and it is always positive. Now what is the grain boundary energy? Grain boundary energy is the interfacial free energy per unit area of the grain boundary, that is Gxs is known as gamma gb and agb. Gb is short form from grain boundary. Okay, and also the unit of gamma gb will be joule per meter square, because the surface energy, the unit is surface energy per area, so joule per meter square. So here here the next slide is about the interfacial free energy is not the surface tension in case of solid. We have discussed the surface tension in case of liquid and vapor interface. One is liquid and the other one is vapor. There comes the surface tension. But in case of the solid, that is the interfacial free energy is not the surface tension. How this conclusion arrives, we'll see. So in a typically fluid, this is let suppose we are going to take one soap film in the wire frame. Okay, and here the interface between the what fluid and vapor interface, the surface tension arises, and here the surface tension always try to minimize the surface area. So in the fluid and vapor interface, the interfacial excess free energy is the surface tension that tries to minimize the surface area. Here consider the sol film in the wire frame as shown in the figure, and here A is the area of the sol film. If we are going to stretch the film by dA, okay, if we are going to suppose to stretch the film by dA, then the total work done will be gamma dA, and this work done is known as Gibbs free energy. Okay, here if you are going to stretch dA, then the work done will be gamma dA, where gamma is the surface tension and dA is the stretched area. So now, but in case of the solid system, the free energy arises due to two reasons. One is the Gibbs free energy due to the bulk system, and another one is the Gibbs free energy due to the interfaces, that is given as gamma A, where gamma is the interfacial energy and A is the area. Here we cannot say that gamma is the surface tension, because in the case of solid, we will going to see the surface tension and the interfacial energy are not the same. But in the case of fluid and vapor interface, the surface tension and the energy are same. See, now there are the two ways which the interfacial free energy can be changed. Okay, one is here G naught is the here Z naught is the free energy at the buck. Okay, and here the gamma is the interfacial energy and A is the area. If you are going to keep constant gamma and keep changing A, there will be change in Gibbs free energy. Also, in other words, we can say that if you are keeping A constant and gamma changing, two cases can be happened. Okay, by changing A surface area and keeping gamma constant, and another one is by changing gamma, that is surface energy, and the A will be kept constant, so that we can change the Gibbs free energy. But in the case of, we see that if d gamma is 0, then the equation will be dg by, if okay, let one assumption we are taking that d gamma is 0. So this will be 0. Next, the Gibbs free energy will be gamma dA. That means if you are keeping surface energy, interfacial energy is constant, surface tension is constant, and by changing the area of the grain boundary, so that the Gibbs free energy can be changed. So we can say that the interfacial energy here is the same as the surface tension. We can see if we are one take the assumption that d gamma is 0, then the interfacial energy will be the surface tension. But in case of solid, the surface tension is not the same as the interfacial free energy. Now, bond breaking model. What this model tells about and how, why this comes behind? Because bond breaking model is the model, it tells about, see, when the two materials are come together, their one bond will be breaking and another one bond will be made. Suppose this material, let A, and another one is this material of B. Okay, so when they come to the in material A, there will be AA bond. In material B, there will be BB bond. When they are put together, they will form the new material of AB bond. Okay, so these AA bond and BB bond will be breaking down to form the new bond, that is AB. So at the time of breaking down of a bond, the energy is lowered. The lowering of energy is known as the bond energy. Okay, so let in this section we'll develop the simple bond breaking model to calculate what is the surface energy of a solid. Let's suppose we're going to take one solid that is contact with its one vapor. Okay, so and we are kept one assumption, the temperature will be kept low, so that that is the there will be responsible for the surface energy comes from the broken bonds. Consider the simple cubic lattice. Here the lattice parameter is A, okay, and the surface of unit length, and here the surface the crystalline surface area makes an angle theta with the principal axis of crystal, and we are going to take two atoms. One is that is open circle and another one is filled circle. Okay, this small section is known as the lattice parameter. Simple cubic lattice. In simple cubic lattice means all the lattice points are in the corners of a lattice. Okay, so of lattice simple cubic lattice of lattice parameter A. So now this, let suppose this plane of the crystal is infinite in the direction perpendicular. That means, see, this is the plane. Okay, this is the plane of lattice parameter A and crystalline surface is unit length and this plane is perpendicular. Okay, so in the field, the open circle marked 1 represent the atoms in the bulk, and the bulk atom has formed the 4 bonds. As you can see, this is the atom in the open circle, and this atom has made 4 bond, and this atom filled circle has formed 2 bond. Okay. In the out of 4 bond, 2 bonds are perpendicular in the direction of plane. That is, another one is above the plane and the other one is below the plane. As you can see, this is the plane. Okay. And here one bond is above the plane and another one is below the plane. Okay. And here the two bonds in the field circle are in the parallel direction to the plane. So what happens? The total in this given geometry, the number of broken bond along the principal axis, the number of broken bond will be cos theta by a square and sin theta by a square. This formula. And this plane, this lattice, this simple cubic lattice, let's suppose in the 3D geometry. So in 3D geometry, total number of broken bond per unit area will be cos theta plus sin theta by a square. Okay. Since the bond strength, let's suppose the bond strength is epsilon, and the total number of bond for the broken bond will be epsilon by 2a square cos theta plus sin theta, and this expression is for internal energy of broken bond per unit length, that is ESB. Okay, this is the internal energy of the surface plane, that is epsilon by 2 here, because the for one bond, okay, for one bond 2 atoms are needed. So epsilon by 2a square cos theta plus sin theta. So a schematic plot, as we can see, that is in the y-axis surface energy, that is ESB, and the x-axis, that is interfacial angle. So we're going to see the expression for the how the interfacial energy is a function of angle of the surface plane. Okay, as you can see, at the angle theta is 0, the interfacial energy is what? Minimum. We can say the curves we can see at theta is equal to 0. That means the interfacial energy or the internal energy other than the theta is 0 is more is more positive than the theta is 0. So we can see the simple bond breaking model, we only consider the chemical part of free energy, and also by considering the bond breaking model we can calculate the interfacial energy, and the expression is epsilon, where epsilon is bond strength of a bond by 2a square, where a is the lattice parameter, and cos theta plus sin theta, where theta is the angle that lattice made with the principal axis. By putting all the value, we can calculate the surface energy, and here which here it is says that only by considering the chemical part, that is the free energy, we have derived the surface energy, that is ESB. In the next classes we'll going to see the what is the boundaries, and different types of boundaries are there, then the solidification, another one is that is most important topic in phase transformation in material. So this much up to today's classes. So thank you so much. Have a great day.